Welcome to video 2 for section 4.5. I just accidentally hit the stop button, so rather than trying to get it all restarted and everything, I just decided I'm going to start a new video. So number 5, we were at this point very quickly. We knew that this was $8 and this was $5, and we knew that if this was the width and this was the length, since the area of 760 was length times width, then I believe I had solved for L, so that would be 760 over W. And we had the cost function, which was 2 walls of length W that cost $5 each, and there were 2 walls of the length, so that would be 760 over W instead, and those cost $8 a foot. And so I was just cleaning this up and got 10W plus, okay, and then 2 times 760 times 8 is 12,160. So that would be 12,160 over W. Now this is the cost, so we want to minimize this, which means we have to take the derivative. So since we're going to take the derivative, the first thing I'm going to do is I'm going to write it in user-friendly form. So that would be 10W plus 12,160 W to the negative first power. So now, taking the derivative of the cost, we would get 10 minus 12,160 W to the negative 2, which of course is 10 minus 12,160 over W squared. And then to put this into a form that we'll be able to either maximize or minimize, we need to get a common denominator, which is W squared. So that would be 10W squared minus 12,160. Now we have to set both the numerator and the denominator equal to 0, understanding that the width being 0, once we set the denominator equal to 0, that doesn't really help us out because we cannot have a negative length, nor could we have 0. So the one that we're really interested in is when does the numerator equal 0. 10W squared minus 12,160 equals 0. Add 12,160 to both sides. Divide both sides by 10, so W squared equals 1,216. And so let's see what we get out of this. So W would equal, okay, let's figure out what all will go into this. Okay. 64 square root, or 64 and 19, so that would be 8 root 19. So the width is 8 root 19, what, feet? Whatever we're talking, yeah, feet. 8 root 19 feet. And then it becomes pretty simple to find what the length would be, because all we have to do is plug that in to the fact that length is 760 over that. And so simplifying that, I'm sure this will simplify. 760 over 8 is 95. So this is 95 over root 19. But that very simply equals 95 root 19 over 19, which happens to equal 5 root 19. And so the length would be 5 root 19 feet. So the width is 8 root 19 feet, and the length is 5 root 19 feet. It is very common to see the 5 and the 8, the fact that those dealt with the price, as part of the minimum and or the maximum. By the way, we did fail to do this. We said this was 8 root 19, so if I plug in the value of 1, and let's see, and the number 1300, let's see what we get. Okay, if I plug in 1 into C prime, that would be 10 minus 12,000, so that's negative over positive, so that's negative, and 1300 will give a positive, so this is actually a minimum here, which is what we were asked to find. Just to clarify that indeed we were finding the minimum and not the maximum. Going on to example number 7, because I'm skipping number 6. Number 7, we have a cost function. C of x is 4x cubed minus 22x squared plus 6,849x. And that's how much it costs to manufacture x items. This is where we need to read the question very carefully. Find a production level, in other words, how many pieces do we fit, that will minimize the average cost of making x items. So the first thing we have to do is find the average cost of doing this. Now in business, when we want average, or actually in math, when we want average, we usually put a bar over what we want to find the average of. So the average of the cost of x would be just this whole thing divided by x, because there's x things being made. So we can do that pretty simply. Let's take 4x cubed divided by x, that's 4x squared. 22x squared divided by x is 22x, and 6,849x divided by x is 6,849. Now we are asked, when will this be minimized? So in order to minimize it, we need to take the derivative. So the derivative of 4x squared is 8x. The derivative of 22x is 22. And the derivative of 6,849 just basically goes off the map. So we need to set this equal to 0. 8x minus 22 equals 0. Or 8x equals 22. So x will equal 11/4. Now obviously we can't make 11/4 of a product. So what we have to do is, first of all, we do want to verify, is this indeed a minimum at 11/4. So I'm going to plug in the value of 1 and the value of, what, 3? 3 will work. So if I plug in 1, 8 minus 22, that's negative. 3 will be 24 minus 22, that's positive. And so this is a minimum, like we want. Now the question becomes, we can't make 11/4 of an object. So the question becomes, do we want 2? Or do we want 3? And what we do here is we just ask, well, which one has the lower average cost? So we're going to do bar C of 2 and bar C of 3. And let's see which one's the least. And whichever one gives us the least here will be our answer. So 4 times 4 is 16. 22 times 2 is 44. Plus 6,849. And 16 minus 44. Okay, 16 minus 44 plus 6,849 equals 6,821. That's how much it costs to create two of these. Now let's look at 3. 4 times 9 is 36. 22 times 3 is 66 plus 6,849. So we take 36 minus 66 plus 6,849, and that equals 6,819. So which one gives us the fewest, the least amount here? It would be 3 items. Whenever it doesn't make sense to have fractions, you do need to take immediately on either side to test which one actually gives either the minimum or the maximum. And the 8th and final. The function y equals cotangent of x minus 2 root 3 over 3 cosecant x has an absolute maximum somewhere on this interval. And we are asked to find it. So, we need to, since it's asking for a maximum, we need to find the derivative. So that's going to be our first thing. Y prime. Okay, the derivative of cotangent is negative cosecant squared of x. Luckily, there's no chain rule required because this is just plain old x. Minus, okay, 2 root 3 over 3. Okay, what's the derivative of cosecant of x? Well, that would be the negative, so that's going to change to a positive, negative cosecant of x cotangent of x. Now, what I need to do now is to set each one of these, or set this equal to 0, and figure out where we go from there. So I'm looking at this and I realize I can pull out a cosecant of x. So that's what I'm going to do. In fact, I'll just pull out a cosecant of x. So the cosecant of x, if I pull it out of this first term, I'm left with a negative cosecant of x plus 2 root 3 over 3. I pulled the cosecant of x out, leaving cotangent of x, and set that equal to 0. So we do have a potential cosecant of x equals 0. Well, the only problem is cosecant of x never equals 0, so that's not going to help us out at all. So we know that part's not going to be taken care of. So hopefully somewhere in here this will equal 0. So negative cosecant of x. Well, I don't want to and don't have to really deal with cosecants and cotangents. Instead, I'm going to deal with sines and cosines. So I need to remember that the cosecant of x is equal to 1 over the sine of x plus 2 root 3 over 3. And cotangent of x is cosine of x over sine of x. And this part has to equal 0. Well, I look at this, my common denominator would be 3 sine x. So all I have to do is multiply this by 3. So I get negative 3 sine x there. And let's see, this would be an, let me get rid of that so it doesn't cause confusion. Negative 3 plus 2 root 3 cosine x. Now the only time that this equals 0 is when the numerator equals 0, and hopefully that doesn't conflict with the denominator. So now all I have to do is say negative 3 plus 2 root 3 cosine x equals 0. Add 3 to both sides. 2 root 3 cosine x equals 3. Divide both sides by 2 root 3. So the cosine of x will equal 3 over 2 root 3. And then to help us out, we're going to rationalize. So this would be 3 root 3 over 6, or root 3 over 2 is what this rationalizes to, which is really nice because then it's a whole lot easier to say, hey, I know what cosine is. Cosine equaling root 3 over 2, somewhere between 0 and pi. Well, we have to remember cosine is positive only in the first quadrant, but not the second. So we only have to worry about the first quadrant. Cosine is root 3 over 2 at pi over 6. And so that's where it's going to occur. Now, just to verify, we could plug this in, and we actually do want to do this, but the cosecant squared of pi over 6 is some negative number, and compare that to, okay, say that would be some negative number here. This would be positive and positive, and so this becomes a positive number. The question becomes, is it bigger than this? Basically what we get is pi over 6 is our cutoff. This is actually positive. I mean, if we plug in, well, 0 doesn't work as a test value, but if we plug in a value down here, we get positive and we get negative. And so this is indeed a maximum, which is what we're asking for. I'm not spending the time to go through that. This is what we did last week and the week before. You just need to make it a point to do that. So the question becomes, where does it occur? It occurs at pi over 6. What value does that give us? Well, we have to go back to the original, and so as the final statement, or the final problem, pi over 6, cotangent of pi over 6, minus 2 root 3 over 3 cosecant of pi over 6, all equals negative root 3 over 3. So where is the maximum? At pi over 6, negative root 3 over 3.